Okay, so again next is, earlier we have seen that your what you call that the development of circuit model. Now you have to see the power across air gap, torque and power output. So before that, regarding principle of operation of induction machine, we have discussed that when the rotor is short circuited, it's this thing. If we assume that rotor is short circuited itself, then it tends to move right in the direction of the stator magnetic field, right. But it will never achieve n is equal to ns, then torque will be actually 0, right. And that interaction between what you call that field flux per pole phi r and your what you call that rotor mmf F2, they are stationary with respect to each other, and the torque will be developed in the direction of your Fr if you see the diagram, right. And that finally your rotor rotates in the direction of the stator magnetic field, that is with speed n, but n less than ns. It cannot be as your what you call, and it reaches a your what you call a steady speed. So now after that we have seen the development of circuit model. Actually things are not difficult, just a little bit of our understanding is required little bit, and that's all. So now power across air gap, torque and power output. Actually why you call power across air gap, that you have a stator, then you have rotor, in between stator and rotor there is a gap, right. And power, actually input power, if you think to the rotor, that is the input power to the stator, right, minus the stator loss. That power will be actually transferred through the air gap, that is where you have that magnetic field, right. So and that will be the input to the your what you call to the rotor. So that's why we call power across air gap. That means power actually is what you call transferred, right, through the air gap, where you have the magnetic field, right. So that's why you call power across air gap. So there is no such confusion of this terminology, that power across air gap, right. So if you look into this diagram, right, we will come to the nomenclature and other thing. If you look into the diagram, this one point is here A and B, right, and this side, this part your what you call, and this is your stator resistance and reactance, this is your core loss component, and this is the magnetizing component, and this is A and this is B. When you make Pg by 3, so it is your per phase power. We will come what is Pm, what is Pg, right. And this side is the rotor side, this is reactance, and this is your R2 dash by S, that your that because your this part is a variable part, it depends on the slip, right. So R2 dash by S. Now this is your actually whatever power crosses that AB, whatever you have made, this is the power actually input to the your rotor side. So and this is your, this part is this is the current I1, this is current I2 dash, and this is I0, quite similar to the transformer circuit, right. Only here it is R2 dash by S, because it is a rotating device, right. So in this case your, now this is the circuit. Now the power crossing the terminals AB, this is the terminal I told you, look at the marker, right. In figure 10 is the electrical power input per phase minus the stator loss, right, that is stator copper loss and iron loss, right. So this is, here it is II square Ri is that your iron loss, and here I1 square R1 is the stator copper loss, and hence is the power that is transferred from the stator to the rotor via the air gap magnetic field. This is known as the power across the air gap, and it is its 3 phase is symbolized as Pg, right. So therefore from figure 10, Pg will be 3 I2 square, I2 dash square into R2 dash by S. If you look at the diagram, this is the Pg, 3 phase power, Pg by 3 means per phase. So 3 phase power will be 3 into your I2 dash square into R2 dash by S, I mean this side, right. So that means the power, that Pg is actually, Pg is the power across the air gap, it is written here, Pg is the power across the air gap, is equal to this 3 I2 dash square into R2 dash, this is basically rotor copper loss, right. So that means this is rotor copper loss divided by slip, right. Therefore or rotor copper loss is equal to slip into Pg, right. Rotor copper loss is equal to slip into Pg, the slip is S, so is equal to SPG, right. The rotor copper, actually rotor copper loss we are representing by PCR, right, is equal to S into Pg, and that S into Pg is nothing but, if you cross multiply, S into Pg is equal to 3 I2 dash square into R2 dash. Therefore here you can write rotor copper loss SPG is equal to 3 I2 dash square into R2 dash. This is equation 20. Now, mechanical power output, that is the gross power, right, that PM is equal to PG, that is your power across the air gap, minus this copper loss, rotor copper loss, right, that will be mechanical power output. So, it will be PM is equal to PG minus 3 I2 dash square into R2 dash, right, but PG is equal to, from this here, PG is equal to 3 I2 dash square R2 dash by S, here it is, this PG you substitute here, this PG you substitute here. If you do so and take your 3 I2 dash square R2 dash upon S common, it will be 1 minus S, and this part is PG, because PG is equal to 3 I2 dash square R2 dash upon S. So, it is, this part is PG, so is equal to 1 minus S into PG. This is equation 21, right. Now, this means that the gross mechanical power output in is 3 times, that is 3 phase actually, the electrical power absorbed in the resistance R2 dash into 1 upon S minus 1, right. So, this is actually what you call, that is that your gross mechanical power output. We will see that from figure 10 can therefore be drawn as in figure 11, where R2 dash is represented as this R2 dash upon S, you can write R2 dash plus R2 dash into 1 upon S minus 1. That means you add R2 dash, subtract R2 dash. So, this part will be the called the load resistance, right. Therefore, if we put that this is my X2 dash, this is my R2 dash rotor resistance, and this other thing left rest of the thing R2 dash into 1 upon S minus 1, actually it is load resistance here, right. So, I mean nothing, this from this R2 dash by S only, from this circuit, that your R2 dash by S only written as R2 dash plus your R2 dash into 1 upon S minus 1. So, this way you can mathematically you can represent like this. So, this is my this is our load resistance. Therefore, this is, it is marked also load resistance, right. This is in figure 11. Now, it is noticed from equation 21 that the mechanical power output is a fraction of 1 minus S of the total power delivered to the rotor. We have seen PM is equal to 1 minus SPG. Here PM is equal to equation 21 1 minus SPG. PG is the air gap power and PM is the mechanical power output. It is 1 minus SPG. So, that thing I am just writing in language, right, of that while as per equation 20 a fraction of S of it is dissipated in the rotor copper loss, right. Even if you come to equation 20, your equation 20, this is equation 20. So, copper loss is equal to S into PG, where fraction of air gap power will be the copper loss, and this is PM will be 1 minus, rest will be 1 minus S into your what you call PG, right. So, basically your what you call this, your it will be PG minus SPG. So, basically it will be PG minus the rotor copper loss, right. So, it is then evident that high slip operation of the induction motor would be highly inefficient. I mean, if you operate at a very high slip, so it will be your what you call that inefficient in this sense. First thing is your S into PG. If S is high, that is copper loss, S is high, then copper loss will be more, right. So, from equation 5 we know S is equal to 1 minus N upon Ns. So, same thing you can write 1 minus omega by omega S also. You multiply numerator and numerator 2 pi. So, it will be 2 pi N is omega and 2 pi Ns is omega is the synchronous speed. Therefore, omega is equal to, you can write 1 minus S omega, that is radian mechanical radian per second, right. This is equation 22. Now, electromagnetic torque, you know, power is equal to torque into angular speed, this relationship you know. So, electromagnetic torque is developed then given by, if it is omega is equal to 1 minus S omega S, both sides you multiply by T, right. That means omega T will be 1 minus S omega S T. If you go back to that the schematic diagram of the stator rotor, where F1, F2, Fr and torque is torque, direction of torque, everything is pointed out. I am not just going back again, right, just look into that, here it is given. So, omega T is equal to 1 minus S omega S T, multiply both sides by T, and you know that this is actually is equal to PM, because PM is equal to omega into T. So, and also PM is equal to, you know, omega 1 minus S PG, right. Therefore, your this torque is equal to that, this one is equal to, say 1 minus is equal to this one, right. That means 1 minus S your omega S T is equal to 1 minus S your PG. So, 1 minus S 1 minus will be cancelled. So, omega S T is equal to PG, therefore, T is equal to PG upon omega S, right. So, let me clear it. So that means my Pg is equal to 3 I2 dash square into R2 dash upon S by omega s Newton meter. This is equation 23. Right. Now next is the computational procedure. So these are the certain relationship you have to keep it in your mind. If you have understood this thing, there is no need to keep it in mind. Easily you can make it. Right. Now computational procedure. So in this case, what we have done is that that coal loss component say is removed, right? And this is your what you call, this is the stator side, this is the magnetizing part, and this is x to that, and this is R2 dash by S, right? So if you just look into the circuit, so this part, this AB part is given, the power across the air gap Pg, whatever I have explained, right? AB is given. So if you try to find out what is my this thing ZF, so this is actually it is given ZF, right? Because this is actually series parallel circuit. So this x2 dash into R2 dash upon S, R2 dash upon S plus jx2 dash, right, parallel with jxm. So it is jxm parallel to R2 dash upon S plus jx2 dash. If you make it equivalent, say if you make Rf plus jxf in this form, you can write, you can separate real, after making this computation you can separate the real and imaginary part. I am not doing it, I request you please do this, right. So this is, this you can make it, already you have studied that single phase AC circuit, same thing. So Pg is equal to, now this is Rf plus jxf. So Pg is equal to your 3 I1 square into Rf, because when you make this your what you call, when you make this equivalent of this one, right. So power across the air gap will be 3 I1 square Rf, because at that time I mean if I make it here, so at that time what will happen, you will make an equivalent circuit. This is my R1, this is my X1, and this is my Rf, and this is my Xf, right. So and this is your circuit is closed, circuit is closed, and this is the current, this voltage is the voltage V, and this is the current flowing I1, right. So this is my R1, this is my X1, this is my Rf, and this is my your Xf, right. So J I am not putting Jx1, Jxf, it is understandable. So that means your what you call that Pg will be this point actually, this point is A and this point will be B, right. So Pg actually the same I1 current now flowing after making this your what you call equivalent one. So same I1, so Pg will be 3 I1 square Rf, right, because this is my Rf. Here it is small Rf I have written, so better you make a small Rf, right. So I mean there should not be any confusion, Rf is equal to small Rf, right. So this is small Rf, 3 I square Rf. So let me clear it, right. So that means, and torque is equal to Pg upon omega s. So you can write 3 I1 square Rf by omega s. Look, here it is, here it is small Rf, here it is small Rf. So there should not be any confusion, right. So this is equation 24. So that means next is the torque slip characteristic. So in this case what we do, the expression for the torque slip characteristic easily you can obtain by finding Thevenin equivalent of the circuit to the left of the AB in figure 12. So this is your figure 12, this is our figure 12. So if you trying to find out the your what you call Thevenin voltage and your what you call Thevenin equivalent impedance, as if this side, as if we have studied in your say the maximum power transfer theorem or your Thevenin's theorem we have studied, no, maximum power will come later. So Thevenin's theorem we have studied. So that your what you call the branch which are interested to find the current, that is taken out. After that we computed Thevenin voltage and Thevenin impedance, right, or for DC circuit Thevenin resistance, right. Same way we will do it. So left side of this circuit we will see this, that is why arrow is marked like this, left side of this one, right. So if you do so, look at the circuit again and again. I am not going to the circuit. When you listen to this, you please draw this simple circuit and the way it has been drawn here, and accordingly what you do, that your this thing, that find out Z Thevenin, it will be R1 plus Jx1 parallel to Jxm. So its equivalent is R Thevenin plus Jx Thevenin, right. Once you get R Thevenin plus Jx Thevenin, right, then what you do, that you compute your what you call, you compute the current. So V Thevenin will be V into Jxm upon R1 plus Jx1 plus Xm. So in this case what happened, that as soon as you, I mean it is something like this, this side we are interested, so forget about this one, as if this side is not there, because we have to calculate the V Thevenin means the voltage across your what you call your VAB, right? What will be the voltage here? VAB is equal to V Thevenin. So in that case, if this is not there, say it is not there, say current is flowing, say this is my I, right? Therefore my I is equal to, forget about other thing, all this is part not there, this is not there, nothing is there. So I is equal to actually V upon your R1 plus J x1 plus xm. This is my I. Therefore V Thevenin or VAB is equal to this is my Jxm. Forget about this one, nothing is there, this part is not there, only I am considering this series part, right. So my V Thevenin will be is equal to, this is xm, so this is the reactance xm into this I, so that means into V divided by R1 plus J x1 plus xm, right. That is my V Thevenin, right. This is my V Thevenin. So same thing I am writing here. This V Thevenin is equal to V J xm upon R1 plus J x1 plus xm, the way I showed you. So this is equation 25. The circuit then reduces to figure 13, in which it is convenient to take V Thevenin as the reference voltage. Now it is the Thevenin equivalent. This is my V Thevenin, this is my R Thevenin and X Thevenin, and this R2 dash, this is R2 dash by S actually, this is your R2 dash by S, this is R2 dash by S, this R2 dash by S we are writing like this, same circuit R2 dash plus R2 dash 1 upon S minus 1, this is my load resistance part, right. And this is shown a variable as because this S can change, because slip can change. So this is R Thevenin, X Thevenin, and this is the point AB, and then this is connected. Basically it is X2 dash R2 dash by S, but R2 dash by S we have written like this, right. So this is my I2 dash, the current, and this is my voltage V Thevenin, understandable, right. So now from figure 13, if you write your I2 dash is equal to, then you can write your R Thevenin plus R2 dash by S plus J X Thevenin plus X2 dash, right. And if you do it and take the magnitude of the current and then the square, then you will get I2 dash square is equal to V Thevenin square. Already we have studied single phase circuit, directly we are writing the magnitude of this current I2 dash square is equal to V Thevenin square R Thevenin plus R2 dash upon whole square plus X Thevenin plus X2 dash upon whole square. This is equation 26. Now we know torque is equal to 3 by omega s into Pg, right. Sorry, torque is equal to your Pg upon omega s. So Pg is equal to 3 I2 dash square into R2 dash s or omega s. So this is my 3 upon omega s. Then I2 dash square, from this expression you substitute here, you substitute here into your R2 dash by s. So this is my torque expression. This is equation 27, right. So if you look into the equation 27 is the expression for the torque developed as a function of voltage and slip, right. For a given value of slip, if slip is known, the torque is then proportional to the square of your voltage, that is Thevenin voltage, right. If slip is constant, if you suppose slip is given, because all other parameters will remain constant. So the torque slip characteristic at fixed voltage is plotted in figure 14. So actually we will learn little bit only about motoring part, braking part or generating part. It is given, but we are not interested into that. So this is I have taken from a book, this diagram. This part actually is a motoring part, it is written, this side braking part, and this is braking mode, and this is generating mode, and this is motoring mode. So we will not study generating mode, we will not study braking mode also, only this part. So we know one thing, that slip is equal to your ns minus n divided by ns, right. Look at this diagram. The speed is in this, speed is like this, and slip is direction is this way. Now when n is equal to, say your n is equal to ns, suppose when n is equal to ns, then slip is equal to your what you call that slip is equal to 0. So here it is for 0 slip is equal to 0, and this side and when your n is equal to 0, that is the standstill condition, at that time slip is equal to 1. So when n, this is my n is equal to 0, this is my n is equal to 0, and this is the plate that s is equal to 1, right. That is why speed is this direction and slip is your this direction. If slip is moving from right to left and speed is your what you call left to right, right, because speed is increasing means that your what you call this, if suppose if n is increasing, So, if you increase the speed, so when n is equal to ns, so this is the plot that sleep is equal to 0. So, sleep is this way, and when n is equal to your what you call your 0, that is standstill condition, sleep is 1. So, it is 1 and here speed is 0. This side need not bother, this side in braking mode and this side is generating mode. Little bit explanation only will be given and that is all, right. And at this point when sleep is equal to 1, so you will find whatever torque it is, this is the starting torque Ts, right. And another thing is that this is this sleep, it is actually given, it is we write like this S max T. I mean this is the value of sleep for which that this torque is maximum, this is called breakdown torque, right. So, this is the value of sleep for which the torque is maximum. So, we write S max T, the max T means this is the value of sleep for which torque, it has maximum torque, and this is called your breakdown torque, and this is actually some point here full load operating point. So, at the low value of sleep you will see this region actually you will find something like a straight line region, right, and you will find that machine will operate in between your what you call this point to this point, the sleep value, right, somewhere it is full load operating point. This is this is your what you call the torque slip characteristic if you draw, right. So, and this side we will only give because I have taken from a book. So, when I am showing it, I think for the sake of completeness I have to show this one, that is why little bit of write up is there, but I am not explaining that, right, because at this first year level there is no need for when you go to the second or third year you will learn much more than this one and everything in detail, right. So, that is what I said. Sometimes this T max we call breakdown torque, sometimes we call it as TBD, that maximum torque, sometimes we call TBD, right, that breakdown torque, this one the maximum torque, right. So, that is why some write up is here. The motoring mode when sleep will lie in between 0 and 1, from this diagram you see sleep will lie in between 0 and here it is 1, right. So, for this range of sleep, the load resistance in the circuit model figure 13 is positive. Obviously, that is the mechanical power output or torque developed is in the direction in which the rotor rotates, right. Also, at S is equal to 0, torque is your what you call 0, right. If you come here, this is my S is equal to 0. So, at this point torque is 0, right, because this y x this side is torque and this is the speed or sleep. So, when this is your torque is 0 at this point. So, the torque has a maximum torque I told you called the breakdown torque TBD. I told you at sleep S max T, the motor would decelerate to a halt if it is loaded with more than the breakdown torque, right. So, another thing is at S is equal to 1, that is your standstill condition, when the rotor is stationary, that is standstill condition, torque corresponds to the starting torque T s. I showed you in the diagram. For normally designed motor, the starting torque will be less than your breakdown or maximum torque, right. So, the normal operating point is located well below TBD, that is the maximum torque. The full load sleep is usually 2 to 8%, right. So, the TBD is the maximum torque, right, and the torque slip characteristic for no load to somewhat beyond full load is almost linear, right. So, I showed you the linear portion. So, another thing is this is actually just for the sake of completeness, generating mode when sleep is negative. So, negative sleep implies rotor running at super synchronous speed n greater than ns, that means motor is running as a generator, right. The load resistance is negative in the circuit model of figure 3, which means that the mechanical power must be put in while electrical power is put out at the machine terminals, only this much. More details you will learn in your machine course for second or third year. And braking mode when sleep greater than 1, the motor runs in opposite direction to the rotating field, that is n less than 0. Negative means it is running in the opposite direction, right, absorbing mechanical power, that is braking action, which is dissipated as heat in the rotor copper, right, only this much for first year level, nothing else. Next is maximum or breakdown torque, how to find out. So, from equation 27, this is my equation for maximum torque dt upon dc is equal to 0, for which you will get S is equal to S max T. If you set dt upon dc dt upon ds is equal to 0 and simplify, you will get S is equal to actually S max T is equal to R2 dash and divided by under root R Thevenin square plus X Thevenin plus X2 dash square. This is equation 28, right. Now, if you substitute this S is equal to your what you call S max T is equal to this much in this expression, if you substitute here and simplify, you will get T is equal to T max is equal to 3 upon omega s into all these things, right. I mean 0.5 V Thevenin square divided by R Thevenin plus root over R Thevenin square plus X Thevenin plus X 2 dash square whole square. This is equation 29. So, equation 29, from equation 28 can be observed that the maximum torque is independent of the rotor resistance, right, R 2 dash, while the slip at which it occurs is directly proportional to it, right. So, that means if you look at here, the slip S is directly proportional to R 2 dash, right, and this is and this part is independent of the rotor resistance R 2 dash, right. So, this is equation 29. Next is the starting torque. At start, slip is equal to 1, right. Therefore, from equation 27 you put S is equal to 1, then you will get this is the expression for the starting torque. Starting torque increases your what you call by adding resistance in the rotor circuit. If you add resistance in the rotor circuit, then this is actually R 2 dash is here. So, naturally it can be increased. From equation 28, the maximum starting torque is achieved for S max T is equal to 1, that is R 2 dash will be equal to root over R Thevenin square plus X Thevenin plus X 2 dash square. For equation the maximum starting torque is achieved, that is from equation 28. If you come to that, the maximum starting torque can be achieved, right, if you said S is equal to 1, right, because this is the slip expression for maximum we got. So, and start slip is equal to 1, if you put S is equal to 1, then your what you call then your the starting torque is achieved for R 2 dash is equal to root over R Thevenin square plus X Thevenin plus X 2 dash square, right. That is your from equation 28. This is my equation 20. This is my equation 28, right. And from equation 26, then I 2 dash will be V Thevenin upon root over this expression. This we know, right, already we know. So, at start S is equal to 1, when slip is equal to 1. So, I 2 dash the starting current will be V Thevenin up here you put S is equal to 1, here you put S is equal to 1. So, this is the expression. I mean everything is straightforward, just you have to keep it one or two things in mind, and rest is solving like your 3-phase circuit, right, sorry, single phase circuit, right. So, now from equation 33 it is clear that starting current will reduce, right. So, next is this indeed is the advantage of the slip ring induction motor, in which a high starting torque is obtained at low starting current. Now, an approximation. Now, we will go for approximation. Now, sometimes for getting a feel, that is a rough answer of the operational characteristic, it is convenient to assume that the stator impedance be negligible, that is R Thevenin is equal to 0 and X Thevenin is equal to 0. If you neglect that is figure 13, you go back figure 13, I am not going. In that case, what will happen? You will find V Thevenin is equal to V. Here I am written, see figure 12, figure 13 and equation 25. Please go back to that. Just with this assumption you put it there, right. And you substituting R Thevenin 0, X Thevenin 0, and in equation 32, you will get I 2 dash is equal to V upon root over R 2 dash upon S square plus X 2 dash square. This is equation 34, right. So, substituting R Thevenin 0 and X Thevenin 0 and V Thevenin is equal to V in equation 27, you put it, you will get torque is equal to 3 upon omega s into V square into R 2 dash upon S divided by this expression, right. So, this is equation 35. Now, also S is equal to S max 2, in that case if you do so, then S is equal to S, it will become R 2 dash upon X 2 dash. If you, I mean based on this assumption, you substitute those your S max T, your what you call expression, you put R Thevenin 0 and X Thevenin 0, you will get S is equal to S max T is equal to R 2 dash upon X 2 dash. So, this will be required for sometimes for solving numericals. Therefore, rotor resistance by standstill rotor reactance and T maximum torque, if you put in that expression, you will get 3 upon omega s into 0.5 V square upon X 2 dash. This is equation 37. And similarly, in that expression of the starting torque, if you put the same thing, only R Thevenin, X Thevenin 0 and V Thevenin is equal to V, you will get starting torque is equal to 3 upon omega s into V square R 2 dash upon this one. This is equation 38. This is first we develop and then we make some simplified assumption, right. So, maximum starting torque S max T is equal to 1 is achieved under the condition R, in this case R 2 dash is equal to X 2 dash. I mean if you assume S is equal to 1 at starting, then it will be R 2 dash is equal to X 2 dash, right. So, and T starting maximum, if you put in that expression, T max will be 3 upon omega s 0.5 V square upon X 2 dash. So, these are all simple things, just put one upon another and you will get this expression, right. So, some approximate relationship at low slip. So, around the rated full load speed, slip of the induction motor is very small, right, such that R2 dash upon S much greater than X2 dash. So, in this, so that X2 dash can be altogether neglected. So, in a simplified analysis, therefore, equation 34 then simplify to I2 dash will be SV upon R2 dash. I mean, we are neglecting X2 dash, because we are assuming R2 dash by S is much greater than your X2 dash. Further simplification, and then therefore, I am not going to this equation again and again, just you write and put it, you will get it, right. And similarly, equation 35 then simplifies to, based on this neglecting, I will put X2 dash is equal to 0, and that is all, right. So, then T is equal to 3 upon omega s, you will get SV square upon R2 dash. This is equation 41. So, equation 41, it can be observed that the torque slip relationship is nearly linear in the region of low slip. When slip is very small, then torque slip relationship is quite more or less linear, right. So, with this, that maximum power output. Now, although maximum power we will see, but it is not valid for induction machine, right. You will see this. See, the speed of the induction motor reduces with load, the maximum mechanical power output does not correspond to the speed, that is the slip, at which maximum torque is developed. For maximum mechanical power output, from figure 3 condition will be, we have seen that your what you call in the maximum power transfer theorem, say in the DC circuit we have seen, AC circuit we have seen. So, in that case, the load resistance, this is load resistance, R2 dash is equal to 1 upon S minus 1, it has to be equal to your R Thevenin plus R2 dash square plus X Thevenin plus X2 dash square. You go to figure 13, right, and figure 13 R2 dash and this thing has been separated, right, and you just look at the circuit that for maximum your what you call mechanical power output, this load resistance must be equal to this one, but it is physically not possible. So, maximum power output can then be found corresponding to the slip defined by equation 42. However, this condition corresponds to very low efficiency and very large current, and is well beyond the normal operating region of the motor. So, it is physically not possible. You use maximum power transfer theorem, go to figure 3, and from your intuition you can make it, right. We have also seen that your for maximum power transfer theorem in DC circuit, that R load is equal to R Thevenin, isn't it. So, here also, because R2 dash is added, X2 dash is added. So, here it is AC circuit. So, that is why impedance part is there, right. So, now, okay, thank you very much. We will be back again.